nanohub.org. Online simulation and more for nanotechnology.
All right, so good afternoon, everybody. Today we're really happy to have with us Professor Sunil Bhave from Cornell University. Sunil is a very well-known researcher in the field of MEMS and photonics, and he got his bachelor's and PhD degrees from Berkeley. That was in 1998 and 2004. So he's been with the faculty at Cornell University since October of 2004, and he has received a lot of honors and awards. I'm just going to mention the NSF Career Award in 2007 and the DARPA Young Faculty Award in 2008. A lot of his students have also received a number of awards. IEEE Photonics, Ultrasonics, and IDM are just three of the conferences that Sunil's work has been recognized to his students. So we're very fortunate to have him here, and so thank you also for attending, and let's give a warm welcome.
Thanks, Dimitri. It's great to visit. I'm told that last week was really bad to come to Purdue, but this week is supposed to be nice, and it is fantastic. Today I'm going to talk about the work going on in my research group at Cornell University on trying to combine micro-electromechanical systems, MEMS, with silicon photonics, and what we are trying to work with them. Just to give an idea, when I first started at Cornell, I started working on RF micromechanical resonator structures, trying to make, let's say, ladder filters, some mechanical filters, vibrating transistor devices, some interesting MEMS resonators, plus RF MEMS switches for sort of phased array applications. And this is because I came from that background. It was the low-hanging fruit that I could attack immediately. But as we start, you start getting into the academic role, and you start expanding and finding other applications of your research. So I just put a collage of some of the current projects that are ongoing in my lab. First, I'll talk about the projects that I'm not going to focus my talk on. One of them is trying to couple MEMS resonators with spin-torque oscillators. Spin-torque oscillators are microwave oscillators that have been shown to have octave tuning range, but maybe they are not so very good in terms of jitter or phase noise characteristics. And so maybe we can couple micromechanical resonators with them in order to make some low phase noise, yet octave tunable oscillators. Second project is a little bit more far out, is trying to couple cold atom systems with micromechanical devices such as this 3D goblet here. And this is mainly for the purposes of fundamental study of interacting atoms with membranes or MEMS resonators, but also with the eventual goal of trying to make a chip scale sort of inertial sensor out of this system. The third one, which we already got some great results out of, is trying to couple MEMS resonators. Here's an aluminum nitride transducer with nitrogen vacancy defect centers in diamond. And this is for manipulating the nitrogen vacancy defect centers to try to manipulate qubits in the diamond systems. There are some applications on that as well, including spin squeezing or state control using mechanical strain. So all these are, as you can imagine, far out topics that are fundamentally driven and funded by NSF. On the other hand, the topic I'm going to talk about today involves a very mature field of coupling micromechanical resonators with silicon photonic resonators to try to demonstrate low phase noise opto-acoustic oscillators. And so I'm very happy to talk with you guys afterwards about these topics, but today I just chose one of them and focus on this particular one here. So before I start, I want to give credit where credit is due. Everything that I'm going to talk about today is the work of these 4 graduate students. They really put in the time and energy in order to make these things happen. And you can see some of the monumental work that went into not just the design and testing, but more importantly, the fabrication of some of these optomechanical systems. So let's start with defining the problem. The problem is very simple. The problem is we have a MEMS resonator. Here is a picture of a comb drive, which was first probably demonstrated by Bill Tang and Roger Howe at Cal in 1989. It involves a shuttle, a proof mass and a shuttle that is, say, in this case, vibrating up and down along the vertical direction. You have a pad down here where you can apply an AC signal, And if that AC signal is at the right resonant frequency, it's going to sort of ping this device, and this device has a very high mechanical quality factor, so it rings up. As it rings up, this sort of capacitor here is going to change its capacitance, and you're going to get motional displacement current coming out of that capacitor. That's going to be measured out of this pad 1 here. So the electromechanical transfer function that I'm trying to measure is this I out over the input voltage signal. And that's going to look like some kind of a biquad response, where there's a very high resonance, which corresponds to the very high quality factor of this mechanical system. And when you operate this comb drive at, say, 20 kilohertz or so, you get extremely large signals, because you get very large motion, and that gives you very large displacement current out of this sense capacitor. So you get very large signals out of this. Now, as you scale this device, let's say from 20 kilohertz to, say, 200 megahertz, maybe going towards 2 gigahertz, a lot of things go in the wrong direction. First of all, the structure starts becoming very small. It's no longer 200 microns, but more like 2 microns in dimension. What that means is it doesn't really move as much. It's mechanically extremely rigid or very stiff. So the actual signal that my displacement sensor can measure here is going to be significantly reduced. So that sort of shows itself as sort of these peak heights reducing as I scale my resonator to higher frequencies. An even bigger problem occurs because as this structure becomes very small, you'll find that this pad 3 and this pad 1 start coming very close to each other. Essentially, the drive and sense transducers are very, very close to each other. And the shunt capacitance between the drive and sense pads through the resonator, under the resonator, over the resonator is going to start dominating. And at high frequencies, that capacitance is very large, or the impedance of that capacitance is very small. So the feed-through current, the current that I'll get simply due to those fringing fields, is going to increase as I go to high frequencies. At around 100 megahertz or so, you'll start seeing the typical micro electromechanical systems. The feed-through signal can actually mask out any of the electromechanical displacement signal that we are trying to measure out of our system. And this system doesn't really work as an electrical system anymore. And this is one of the biggest challenges that we faced as we started scaling our devices to the gigahertz regime. So why do we persist with this? Because some people will say, well, stop doing electrostatics. Work with body forces, bulk forces, piezoelectric forces. And they will give you much larger forces, which will give you much larger displacement currents, and you will get much larger signals, and you will avoid this problem. But the advantage that electrostatics gives you is that it's actually an actuator at a distance. It gives you this independence where the actuator is different than the resonating element. And so it allows you to sort of design the two of them independent of each other. You can choose a resonating element to have extremely high mechanical Q, for example, without having to worry about how am I going to attach a transducer to it. And this is what allows us to get very high mechanical Q, and that's important because in the end what we are after is the frequency Q product, the FQ product, which essentially determines how good of an oscillator I can build using this system. So we wanted to stick with the electrostatics, but we wanted to somehow get rid of this feed-through signal problem that was sort of facing us. So there are some electrical engineering techniques that we can use simply using differential circuits or trying to have shunt paths sort of grounded out, shielded electrodes, and so on and so forth. And we tried all of that. And eventually we said we were sort of running out of all possible ideas. And it was around that time that I was walking by the hallway and I noticed that Michal Lipson's group in Cornell, who works on silicon photonics, there were pictures, SEMs of her devices on her bulletin board that looked rather similar to some of the ring resonators, some disk resonator devices that we were building in our lab. They seemed to be made out of SOI wafers. They had 2 micron silicon. They had some buried oxide layer. There was some timed etch release that was happening. And we were like, well, what if we take a mechanical resonator and couple it to a photonic resonator? So the idea we pitched forward to DARPA, this was part of the Young Faculty Award program, was saying, I'll make a MEMS resonator and in the same layer, couple it to a photonic resonator. I'm going to drive the MEMS the way I know it, using RF signals and air gap electrostatic actuators. But I'm going to measure its displacement not electrostatically, but optically. And the way I'm going to do that is I'm going to have a waveguide going by this optical resonator here, and this light is going to be coupled to this optical resonator, and this device vibrates, the light is going to get modulated, intensity modulated by the vibrating frequency. I can have a detector at the very end that sort of demodulates out the mechanical signal, and I can measure the overall electromechanical response of the system. To bring everybody on the same page, let's see how individual elements in this system operate. First one is a MEMS resonator. It's actually very simple. It's essentially a disk that is vibrating in its dilational mode. It's like your eyeball, right? It's like dilation of your eyeball. It's just expanding and contracting. The mathematics of it is actually very simple. It's just basically given by the Bessel function math. You can find out all the radial mode of vibration of this thing, right? And they're very close to just being simply 1 gigahertz, 2 gigahertz, so on and so forth. And so that was straightforward on the MEMS side. One thing you notice, as the disk vibrates radially, it's also changing its circumference. So that becomes important in the next part of the side of the device, which is the photonic resonator. In the photonic resonator, as the disk expands and contracts or dilates, its circumference is changing. What that means is that the optical path length that the photons are traveling along the circumference of the disk is changing. It's getting modulated. So if I had some light being swept through and I couple this light to this sort of stationary disk, I get a transfer function where the light couples in and does not couple in. It couples in when integer number of wavelengths can fit in the circumference of the device. Otherwise, it doesn't couple in. So I can do is I can simply maybe expand the device. So pseudostatically, I just expand the device. So I can sort of get my laser in resonance with the optical mode. Or I can contract the device, in which case my laser will go out of resonance with the optical mode. And if this device is breathing, radially vibrating, then it essentially can do this back and forth. So I essentially get intensity modulation of any laser that I put in at the output of this waveguide. So once we have these two systems in place, now let's work and fabricate this thing. Seems pretty easy enough. And Suresh, who was the first student, I said, well, let's do this. How hard can it be? We already know the MEMS. The photonics group has already figured out the photonics. Let's make this. And so we came up with a process flow. So just, this is the nano center. So I think everybody will appreciate some of the good work as well as challenges that we face here. We start with an SOI wafer. Mind you, it's a custom-made SOI wafer. That's a 3-micron buried oxide. I think if you're doing photonics, you're probably aware of it. You oxidize the silicon layer to form your hard mask, and this is your electrode pattern. Right? Those are the MEMS electrodes, the MEMS resonator, the photonic resonator, and the waveguide. So I'm just transferring that pattern into the photoresist. That pattern gets transferred from the photoresist onto the silicon dioxide hard mask. And then I transfer that hard mask pattern into the silicon device layer using a chlorine ICP etch. Go a little bit further to expose areas of the buried oxide. And here comes one key step, which is, maybe you guys are wondering about it already, but we'll protect half of the device. We protect the photonic disk and the photonic waveguide with thick photoresist and didn't do an ion implant. The ion implant will allow the electrostatics to be heavily doped. And electrostatics require heavy doping because we need free charges on the structure to move back and forth, that generating the actuation of the device. But if you have any kind of free electrons or heavily doped silicon on the photonic side, the electrons or the doped silicon can potentially cause extinction of the photons earlier, effectively affecting your photonic performance. So this becomes an important step. And once you do this, you then strip off that blank photoresist mask, put on your real release mask here, which is a square window, and then do a timed BOE release that will release the oxide, sort of leaving the MEMS structure suspended. Seems reasonable enough. It took us about 2 years to realize this. And here's the RF electrodes. Here is the MEMS resonator right here. Here's a mechanical coupler. Here's a photonic resonator. And that's the waveguide that is going by. No, so why 2 years? It ends up that we're no longer just making a MEMS resonator or just making a photonic device. the requirements are a little bit different for both, and we have to get the yield right and the maturity of the process right, such that you get 100 nanometer air gaps here, you get a beam that is very well defined, you get 130 nanometer air gap here. You want to make sure the waveguide is designed in such a way that the photons go right through without leaking into the anchor. So the anchor has to be optically preventing any photons from leaking out, but mechanically it should be robust enough to suspend the waveguide. So you have to design an MMI structure there. And last but not least, and the E-beam guys will appreciate this, is you have a different fill pattern. There are a lot of empty areas here, there are not many empty areas there. So you have to do some correction techniques in order to compensate your mask. And that went some challenges. You can see the etch holes need to be properly designed because of the timed etch to make sure you have an oxide pedestal anchor left behind. You still are left with some white residue, as you can see here, which took us a while to figure out as well. So once you have this thing done, then maybe how does this look? To give an idea of size scales, the actual device is probably around 20 by 10 microns or something like that. It's very small. But we are doing microwave photonics, so we need to have proper microwave routing. You have your GSG bond pads on the MEMS side. You have your optical grating couplers on the optic side. And how do we test this? We basically take our RF probe station and we replaced one of the RF arms with a fiber optic arm. So we just have a silicon chip, and just like we test our RF components, we just step through and measure the performance of our device. So you just RF signal coming in, optical signal coming in the other side. So everything I show is measured at room temperature and pressure unless I specify otherwise. For us, the big learning curve was not the MEMS, it was the photonics. So we want to make sure the photonics works properly. And so here is the transmission response on the optical resonator. You can see the broadband sort of filtering function of the grating couplers. They act like sort of low Q filters. And in the middle of it, you can see these optical resonance peaks. These are the resonances of the optical disc. If you zoom into one of them, you find that we get a pretty reasonable optical quality factor, around 50,000. This was a concern because if you remember on the SEM, there is this stub here. And if you have photons going around in a circle along the very edge, it might be a scattering point for the photons that would effectively hinder the quality factor. But we found actually there are particular optical modes that are just deep enough from the edge where that particular coupler does not really affect the performance of the device. So it's about choosing the right optical mode. And so if you model it, you can see, for particular wavelengths, you'll find that the effective refractive index of the disk mode matches the effective refractive index of the waveguide mode. And this is where you're going to get critical coupling between the waveguide and the disk resonator. For the EM guys, this is really, I'm just doing impedance matching between my input electrodes and my resonance cavity. Right. So we have this in place. And so now we want to test our optomechanical system. Hook it up with a network analyzer. We have an RF signal going into the device. This is the electrostatic drive, and so we have a DC bias to linearize the actuation. When this structure is actuated, this will vibrate, that will vibrate. So if I have a laser coming in, it's going to couple to this photonic resonator, come out, then the photodiode will essentially down convert and give me back the RF signal, and I can put the RF signal back in the network analyzer. So it's a simple two-port measurement system. And once we got everything right, we found that this thing works like a charm. This is the effective network analyzer transfer function, essentially the gain of the measurement from the input RF to what's coming out of the photodiode. You can see the mode of vibrations. This is a dilational mode of the two disks. There's an in-phase mode and out-of-phase mode of the two disks. So that you can see sort of two peaks here. You can see the second harmonic of it, the third harmonic of it, fourth harmonic. You can actually keep on looking at it until the 10th harmonic or so. These are the modes that we were targeting. There are some modes that you are surprised to see. This is the wine glass mode, which has certain applications later on that I'll talk about. There are these low frequency modes, and initially we were wondering, what are those modes coming from? It turns out it's actually the floppy waveguide has its own vibration modes that can also be seen in the device. And so what we have really built is an incredibly sensitive chip scale interferometer of our mechanical resonators. Now, folks in the audience who are MEMS people already know of a Polytech interferometer. This is really just a Polytech on a chip. We are really just measuring all the mechanical modes of vibration of our device right in proximity to it. As a MEMS or oscillator designer, when I see a transfer function that only requires 30 dB of loss, and I can order a 30 dB amplifier from many circuits and try to build an oscillator out of this. And so get rid of the network analyzer, buy a low noise amp. For all the cabling, you need to get rid of it, so you put a phase shifter to adjust for all the cabling, and then close the loop and make your oscillator out of this. So simply, and once we did that, we were able to show, yeah, we can see very clean-cut oscillations that depend on the laser power or the DC bias of the actuator, so you know 2 tweaks. One thing we did fix was in the previous transfer function I showed there were 2 resonances, in phase and out of phase resonances, and we have clever design techniques in order to mitigate or attenuate one of the modes while enhancing the other, and you can see clearly here that's one of the modes, that's the other, so the oscillator safely locks to that particular mode. So we have the oscillator, well, it's a sort of this random frequency, 237, and so the challenge to the student was, let's make a gigahertz oscillator. And so going up the learning curve now, things are being stamped out of the clean room, which much faster than 2-year kind of time frame. We swap out from a tethered anchor on the left, which obviously DQ'd our performance, to a balanced anchoring system that allows us to have very balanced high Q mechanical resonators. Instead of disks, we are going with the rings now, because in this case, the rings optical modes and optical properties are defined by the outer radius. So we can choose whatever outer radius you want on the photonic side. On the MEMS side, the mechanical resonant frequency is dictated by the width of the ring. So you can choose your inner and outer radii to be whatever you want, but you can sort of basically decouple the mechanical design from the photonic design. And once we do this, we can start designing resonators that are much higher in frequency. And so we did that, and then we were able to show, okay, now we can close the loop and start making gigahertz kind of oscillator devices. And this is where I called up my DARPA program manager and said, okay, I have something that definitely works, and we have something that has a very good phase noise. So he said, well, good enough phase noise at Cornell is not good enough for me. This has to be verified by somebody else who is a higher authority. And part of the problem with these photonic systems is they're impossible to move out of a lab. But our system was actually portable enough. We just packaged it up, mailed it to NIST, and said, okay, NIST can verify the performance of our device. And so we were able to then demonstrate actually their measurement was better than ours, or rather their measurement system was better than ours. And so you can see all the close to carrier signals are much cleaner in the NIST system than our noisy spectrum analyzer system. But we were able to prove that we have a portable enough system, but has decent phase noise, and we can start using them for other purposes as well. So what happens next? Well, we try to improve on the phase noise that we just demonstrated. There are 2 immediate things that we can do. One of them is we need to improve the transducer in the sense that we need to reduce this gap or come up with a way to reduce the impedance looking from the electrode into the device. The second is, as we scale to high frequencies, the intensity modulation that we are getting out of this photonic resonator, well, it doesn't move as much. So we need to increase the optical quality factor of that photonic resonator so that we still get complete extinction of the light as the device vibrates. So we want to improve the optical Q of this resonator as well. Being an engineer, you want to separate the 2 problems, attack one problem in one way, solve the other problem the other way, then eventually merge the 2 solutions together. So step 1 is reduce the impedance from the mechanical side. In order to reduce the impedance from the mechanical side, you can always go with an array of devices. An array of devices means you get larger transducer area. A larger transducer area means I get more oomph, more energy transfer from the electrical domain into the mechanical domain. We took this idea from Professor Clark Nguyen's paper here at Transducers 2009, where they used a mechanical lever system to couple a large array of MEMS resonators to another resonator at the very tip. Remember, in the optic side, I want very large change in circumference. On the MEMS side, I want very low impedance, very good power handling. So essentially, we thought we could build an array of MEMS resonators to get our low impedance, and then lever it out to very large displacements on the end resonator that will allow me to get very large optical, or rather extinction, and therefore get a very large signal to noise on the optic side. So we built exactly that. And so here is a system of 7 MEMS resonators on one side balanced out to a single photonic resonator on the other side, and you can still see the waveguide going by. Couple of things, you can see the actuators are only around the center 4, not around every device there. And that has to do partially with the routing challenges that a single layer of SOI will provide you. There are certain reasons why this might be there, one of them being momentum balance. Mechanically, you have to be momentum balanced to get high mechanical Q out of the device. So various considerations that went into play in order to make this device. The other thing we found is that as we scale the devices to gigahertz kind of frequencies, our optical time constants and our mechanical time constants started coming out to be in the same ballpark. Of course, they're running at a gigahertz, so the mechanical time constant is pretty straightforward. It's about a nanosecond or so. Now, the photons are circulating in this disk. The photons are at around 170 terahertz, but they have a Q of like 50,000 to 100,000 or something like that. So they're in there for a long enough time. And they might be in there for a long enough time that the mechanical device starts coupling dynamically to the optical performance of the device. And so what we thought was, well, if that's the case, then in addition to intensity modulation of light, we might actually be measuring some phase modulation, some frequency modulation of light. And so that was interesting. So we hooked it up, we drew the same setup, but now we put up a Fabrication Process in there to see those sidebands. Are we seeing those phase sidebands? And lo and behold, yeah, we were able to see mechanically generated sidebands to a pump that is 1 gigahertz away from the actual pump. This is a silicon device that is mechanically causing phase modulation of light. More importantly, we can actually just generate photons on one of the sidebands by adjusting the detuning of the device. Now, granted, the efficiency of conversion is still a work in progress, but just showing the first proof of concept was actually pretty exciting. And so we pitched this as a new DARPA program, so you can try to increase this number a little bit. The other thing to do was to take advantage of this kind of spectroscopy that is available now to us readily. And so, here I plot out the mechanical spectrum from DC to like 10 gigahertz, and you can see the whole thing light up. And so then you get COMSOL is there, and it's single crystal silicon, so everything is very predictable. So you can run COMSOL, figure out all the mechanical modes of vibrations, find out which families they are from, whether the radial family or the wine glass family, and map them out and measure the quality factors of individual modes, their harmonics, the mode families, so on and so forth. Now, why would we want to do that? Is because then you can do your fundamental study of FQ versus frequency. Now, if you have a particular mode family, let's say in this case a radial mode, it seems like it's topping out, sort of around 1E13. On the other hand, the wine glass modes seem to be continuously increasing as I go to higher frequencies. Now, the circuit designer, what this tells me is if I choose a radial mode of vibration, it doesn't really matter whether I design a 2 gigahertz oscillator or a 7 gigahertz oscillator. It's probably going to give me the same phase noise, the same ballpark at least. On the other hand, if I choose a wine glass mode of vibration, and if I actually try to target this one here, I will get much better phase noise out of this device than, say, one of the triangles down here. So it actually pays to go to higher frequency with these devices. So that's what this kind of spectroscopy gave us an insight into. And of course, now what we are saying is we're going to switch from radial vibration modes to wine glass modes and try to lock an oscillator at 10 gigahertz at those frequencies and trying to take real advantage of this FQ scaling. So what are we doing today? We want to make better devices and higher frequencies. We started with rings, but maybe disks are better in terms of packing density, die space constraint. We got some new E-beam that can design We can use it to make some very tiny gaps in our structures. We use ALD alumina in order to reduce the gap sizes, which will further reduce our electromechanical impedance. And also, surprisingly, it acts as cladding and therefore improves our optical losses as well. We start becoming professionals in RF testing. We switch from platinum bond pads to real gold bond pads. So we can really, last but not least, maybe switch from a Santec cavity laser to a real low noise fiber laser. So you make a list of things, I'll slowly go through this. And first things I would like to show is the partial gap coding process. So you have the MEMS resonator, and if you look at from the electrode looking into the device, the transducer efficiency is simply given by this equation here. What you can see here is that that gap square becomes really important. If I make this gap 10x smaller, my transducer efficiency goes up as 100. So it's definitely advantageous to reduce the gap. And so we said, how can we introduce this into our process flow? So you start with our release device. Remember, we want the ALD coding everywhere, so we have to have a release device. And then with the release device, we take this and put it into our ALD machine. So now there is ALD everywhere. It codes the gaps, codes the devices, makes this gap smaller, makes the electrode to gap smaller as well. So you're now getting better transduction on the electrostatic side. Two challenges remain. One is, well, wait a minute. I had metal bond pads, and now I just coated it with ALD. And so how am I going to open up that contact again? And so you can't really spin photoresist on a release chip because it'll break off and fly off. And so we just spray coat the chip with photoresist. So we have a spray coater and we just like literally spray coat 4 micron thick photoresist on the device. The bond pads are relatively big compared to the diagram that is shown here. They're about 100 by 100 microns. So now you can do lithography on this to try to open up this area to remove that coating. But to our surprise, what we found is that when we did the developer, it turns out the developer actually has a little bit of TMAH. And that is sufficient to actually etch away the alumina. So we were worried that our chip will then have to somehow go through some wet chemical processing or some dry RIE etching, and it has all these release structures in there that could be harmed. But actually the developer itself is acting as an etchant to sort of expose our bond pad. And so we were very cutely able to show this coating everywhere. The optics is coated, the MEMS is coated, the gap is shrunk, and we have an exposed bond pad. Sort of get everything. And once we do that, you can immediately see the performance improvements. You can see the black line here is showing the mechanical resonances that that this particular system picked out, and you can't really see any resonances after, say, 2 gigahertz. But once you have the ALD coding, it improves the transducer efficiency, and now you can see resonances much higher. So yeah, definitely this coating helped. And to be quite frank, it was that release of that bond pad which was actually more key than any of the performance benefits. The other advantage was on the optical side, and so we simply put light in and try to measure if this ALD is going to degrade our optical performance. It turned out it didn't. The optical Q before and after the ALD coding was pretty much exactly the same. So our optical Q was not affected. If anything, for some reason, it seemed to have improved our bandwidth of our grating couplers. We will take that any day. So we are very happy that the ALD did not hurt our optics at all. In fact, now we have some evidence to show that if we use it right at the right thickness, it will actually improve the optics as well. The third thing we did is we want to always make sure that your critical couple between the waveguide and the MEMS resonator or the optical resonator. If you don't have critical coupling, then you won't get proper coupling of light. And the E-beam has enough of a variation that there are certain gaps that couple and certain gaps that don't. And so we started using a MEMS actuator to sort of control that gap. And by applying DC bias voltages, we can either couple light in or not couple light in. So we sort of have that extra little tweak such that every device in the array couples light into the resonator. So with all these three handles, then we are able to now start making oscillators that work around 2 gigahertz or so, but now we can start seeing these harmonics all the way going to about 12 gigahertz, and we have pretty good phase noise of these devices up to sort of X band kind of frequencies. So what's the next step? Well, of course, is this power out here is very small. It's around minus 30 dBm. We want to try to get it to around 0 dBm. So we're trying to get more oomph out of the oscillator or improve its figure of merit. So here's how we're doing it. You can start seeing the power of the fabrication technology as well as the student as they mature and start making more and more intricate devices. Here's an array of, I think, 25 devices coupled to one optical resonator at the very end there. If this is not enough, then maybe you make an array of 100. This really shows how far we have gotten since this is 4 years, from 2008 to 2013. This is a millimeter in size. So we're talking about arrays that are millimeter size scale. There are 100 such resonators in there. If you zoom in, each resonator is around 3 to 5 microns in diameter. All of them pretty much the same diameter. And then this is sort of a credit to the student and the E-beam and the proximity correction algorithms that go along with it. And then if you zoom in furthermore, then you can see that everybody has a very tiny gap, around 50 nanometers gap. So you really can go from millimeter size scales to nanometer size scales while maintaining good electromechanical and optomechanical performance of these systems. And so these are some of the devices that are currently being evaluated in my lab. Remember, I said that we'll do a divide and conquer approach, and so we showed you a bunch of array pictures, and this is work in progress. The second part was, can we improve the optical Q of these devices? We found out that silicon pretty much has some kind of a limit, practical limit associated with it. Ali Adibi's group at Georgia Tech has shown Qs of like million, but we could not reproduce those kind of results at Cornell. On the other hand, silicon nitride devices have been shown by various folks, including folks here at Purdue, of showing extremely high optical Q in the systems. And at Cornell, we have a lot of inbuilt expertise in very high mechanical quality factor silicon nitride devices. So we said, okay, maybe silicon nitride is a material of choice. Other interesting properties include working at the wafer scale rather than at the chip scale, and using regular G-line lithography tools instead of E-beam. So there are a lot of benefits to this. So we started with making silicon nitride as a platform. So you start the fabrication process. You start with depositing of silicon nitride on the 4 micron thick thermal oxide. So you have your red silicon nitride, this is a giant thick layer of oxide. You have your mask. You transfer your mask to the nitride, and then you put the PECVD cladding. This allows the light to be well confined within the nitride. Once you have that cladding, you open a window where you want to release the photonic device. Now this is a key step. I could have taken this device and put it in BOE to release the device, but it will undercut laterally a lot. So we sort of etch back as much as a little bit down, so we have a smaller time of release. And that becomes a very critical step, so that when we do a timed release at the very end, the waveguide sections and the other sections of the chip are not released, not attacked by that HF, and only the MEMS structure is released. So we have something like this. Seems simple. Here's a picture of it. Here's a silicon nitride ring. You see the pedestal anchor with 4 suspensions. There's a waveguide coming in. Trust me, I would not show this picture to you if it was shorted like that. So that's just charging from the SEM. And simply you want to see, can we couple light into this? Does it really have decently high optical Q? And maybe what is the mechanical performance if we can see it? So that was our belief. So divide and conquer, trying to make silicon nitride optomechanical systems. Step 1, move away the RF probe tip. There is nothing conductive on the device. So now you're just doing optical measurements. And step 1 is simply to measure the optical response. And we were able to get much sharper optical transitions as we expected out of the silicon nitride. And we got, even at first shot, we got a very high, this is around Q of 200,000, but we got very decent optical Qs all the way to millions, depending on the device and the geometry of the system. So we had the optics in place. And it was around the time that the DARPA ORCID program started, which was essentially using optomechanical forces for heating and cooling of optomechanical systems. Essentially using photons to generate forces onto the mechanical devices. we had a release device that coupled light very well. So of course we would try to see whether we can do some heating and cooling with it. And so yes, we coupled some light into it, and we got we got some RF power out. But then the radiation pressure forces took over, started self-oscillating, and we got some RF signal out. So really the heating, the optomechanical radiation pressure-based heating effects were measured. Maybe this figure does not tell you everything by itself. This is what will tell you, is at low powers, low laser input powers, if I just look at the RF spectrum coming out, I see the mechanical Brownian noise of the device. The Brownian vibrations of that particular mode of vibration are imprinting itself onto the photons, and then you can see it when you down convert the light. That again tells you the amazing power of the light. It's really just an incredibly good clock with very high fast sampling speeds, and I'm able to see the Brownian noise. Now if you choose the correct detuning, there is a particular delay in which the photons enter and the response mechanically, and you can choose it such that you get negative damping effects out of this. So the photons will eventually start pumping energy into this mechanical mode of vibration, and you start seeing this threshold leading to self-sustained mechanical oscillations due to light. So what was just simply Brownian motion, now the photons are imparting energy to the phonons and launching self-oscillations of the device. So you're able to see this threshold as a clean-cut resonance. This is observed by other groups as well. So what's so special about this? What was interesting to me was the phase noise performance. And if you look at the absolute numbers, nothing special here in terms of absolute performance. What was very interesting was it was 1 over f squared all the way. Right? Makes sense. I don't have an amplifier in a sustaining loop that is adding 1 over f noise into the system. It's just a self-oscillatory system. And so it just gives me the 1 over f squared, which is essentially the Brownian noise. The white noise of the mechanical system is being seen. And more importantly, it matched theory extremely well. This was like spot on. We literally ran out of spectrum analyzer. We had to actually get a signal source analyzer, the Agilent SSA, which becomes your best friend for getting these low offset measurements. And we found that actually all the way to about 2 hertz or so, we were able to get f squared. And what limits it, and this is something that is, you eventually do get 1 over f, and that coming from the laser. It's not coming from the mechanics. It's just coming from the laser. You don't have to just oscillate radial modes. This was an example of a radial mode of oscillation, but you start seeing some other interesting modes of oscillation as well. Here is an example of one which is a sort of a wine glass or a rubber band mode. And there are a lot of MEMS applications that are more interesting from this mode standpoint than the radial breathing modes that we're oscillating. So we want to use our sort of MEMS tricks to sort of control which ones oscillate. Right? So because we want to be able to control. And so we changed the suspension design of, say in this case, these two coupled devices where we can choose. We are the choosers, it's not by luck. We can choose whether we oscillate the radial mode or the wine glass mode and not oscillate the other. Right? So if you're making a clock, you probably want the radial modes. If you want to make a sensor, you probably want the wine glass modes. And so you can pick and choose which modes you want. And so that's what was exciting, and now we're pushing this a little bit further ahead. So I showed you oscillators. The first thing that you can say is like, well, okay, if you have an oscillator, and I come from the inertial sensors background, so like, well, if it's so sensitive to displacements, I should be able to just make an accelerometer with it. And so Michal Lipson's group, as well as Oscar Painter's group, had shown this optical disk stack resonator was essentially an optical supermode between 2 photonic resonators. This was a silicon nitride stack or a silicon stack. You can do both. What we did was, instead of releasing both these devices, we sort of just kept the bottom one anchored. So just one anchored, and the second one is free to move. And that becomes sort of the proof mass, that the accelerometer proof mass is just, depending on the acceleration, will either move up or droop down. And that changes the gap between these two rings. That changes this gap, that changes the wavelength of the supermode that's sitting between these two rings. And so we fabricated this device. we didn't have a waveguide coupled into it, so we were using a taper fiber. But by just flipping the device up and down from 1G to plus 1G to minus 1G, we were able to get sort of a change in the modulation index. So if you have the same laser, you'll either get some light out or a little less or a little bit more. But it turns out actually you get quite a bit of modulation, around 22% for plus minus 1G. Just to compare with electrostatic accelerometers that are out there, these days you will get something around the order of 2% modulation for plus minus 1G. So not surprisingly, you get about a 10x improvement in your sensitivity or your scale factor when you're doing this optomechanical sensing compared to, say, electrostatic sensing of these devices. You can say, okay, I can keep on pushing this further. As an engineer, you will say, well, that's too much. That's almost too much sensitivity. What I should be able to trade this off for something else. Something else meaning bandwidth, something else means dynamic range. So there are creative things that we need to pursue that will try to improve its dynamic range or your bandwidth while maintaining reasonable sensitivity. And so that's what we are exploring next. So, so we have this tool set now. Sort of forgot about that oscillator, right? We were going to plug this back into the oscillator. That's because there is no progress on that front. but we have this thing. It's its own project chip by itself. And so let's see what else can it do. And so you have a device that works as a fantastic accelerometer that has a pretty decent phase noise. More importantly, it doesn't have long-term drift potentially. And maybe it also is so sensitive to displacement, it can measure Brownian noise of the structure itself. So really, I have something that should be a tool set that I can use to build all kinds of sensors. And the sensor that I'm most interested in is a gyroscope. So we pitched this program. We said, okay, traditional silicon gyroscopes, or traditional MEMS gyroscopes, are made out of silicon. Silicon has low thermoelastic damping, so the Qs are a little bit lower. It has an anisotropy depending on the crystalline orientation. Typically made in 2Ds and have this problem when 2D structures have out-of-plane parasitic modes of vibration. The preferred mode of transduction is using electrostatics. We have conductors, we can use electrostatics. What's appealing to investigate was, can we make gyroscopes out of non-conducting materials, like silicon nitride or silicon dioxide? Now why? Because they're amorphous, so fundamentally they're isotropic, so it's easier to do frequency matching or mode matching. They have extremely high thermoelastic dissipation, so their quality factors are potentially higher, like you saw in silicon nitride. You can mold them into 3D shapes, and those 3D shapes fundamentally have very little anchor loss. So you have very high Q on the anchor loss side of things. And those 3D shapes also give rigidity against parasitic out-of-plane modes. So that's 3D. And then, oh wait, I cannot use electrostatics, but now I have light that I can couple to this. So it was more opportunistic that I had optomechanics working in my lab, and I wanted to make a gyroscope out of these materials. So let's combine the two and try to make OMG, right? My students argue that I first came up with the acronym and then came up with reasoning for it. So how does a gyroscope work? Maybe in the last couple of minutes. A gyroscope works, there's a mechanical proof mass, in this case, that is oscillating back and forth along the x-axis. Right? Now, if this entire board feels a rotation, say, about the axis out of the plane of the board, so in this case, say, omega z, then you get a cross-coupling term that couples the velocity along x with the rotation of the system about z. And that comes out as a Coriolis force, a fictitious force, that acts along the y-axis because it's just basically x cross z. And that acts as an acceleration of the outer frame. The outer frame deforms due to that acceleration, and you get some capacitive electrodes that can pick off that motion. So it really consists of two parts. There is an oscillator along the x-axis. There is an accelerometer along the y-axis, along the orthogonal axis. And it has a capacitive sensor, hopefully, that is sensitive enough to detect the tiniest of motions along the y-axis. And those are exactly the three things that I showed that optomechanics was capable of producing. Very low, decent low phase noise, but more 1/f² kind of slope oscillators. you have a pretty decent accelerometer with very good sensitivity that can measure the Brownian noise floor of a mechanical system. So we have all the building blocks. The problem was, wait a minute, this is all rectangular geometry, and I just showed you all very nice and circular designs. So, well, you know, there are more mechanical mode families out there. This one is pioneered by Farouk Ayazi's group at Georgia Tech, where this is using a shell mode that uses this as your drive mode and the diagonally degenerate mode as a sense mode. I will spare you the details of how this works, or if you're interested, please read Huri Johari's PhD thesis. But needless to say, these two modes can also be used. And you can see this is the mode, the wine glass mode that I identified with you earlier. And so what we are doing with this is building something like this, which is essentially sort of a 3D shell, like I promised. It's made out of silicon dioxide. And now you can imagine, wait a minute, where is the waveguide? Well, that's coming. And we try to make a 3D gyroscope or an OMG out of this. So I'll summarize my talk. We designed a 1 gigahertz oscillator that has pretty decent phase noise, and we showed that, yeah, we can actually launch optomechanical oscillations with no flicker noise. We have demonstrated a decent accelerometer, and now we're using this oscillator with this accelerometer principle to try to make these 3D OMG devices. And I'll conclude my talk here and take any questions.
Right, thank you.